right, welcome back. So, last time we met through this Lightboard, we had a substantial discovery. It took quite a bit of time, in fact, I believe upwards of like 25 minutes. But ultimately, the result was quite significant because we were approximating the area between a function's graph and the horizontal axis previously, and using the mean value theorem and ultimately a limit as n goes to infinity, where n is the number of rectangles, we got an error-free estimate for the signed area between a function's graph and the horizontal axis, an exact signed area, if you will. And essentially, our primary assumption was that our function little f of x has an antiderivative. So the existence of an antiderivative allowed us to utilize the mean value theorem. It allowed us to go through the computation as we did, and we ultimately computed the exact signed area between the graph of f of x and the x-axis on a comma b to be capital F of b minus capital F of a. So I haven't even sketched in rectangles here because we've let number of rectangles go to infinity. So if you imagine this region filled with even a million rectangles, it would basically be filled completely, let alone if we had number of rectangles as number of rectangles go to infinity. So it's not inappropriate, frankly, to draw this region with no rectangles sketched in, because the rectangles that we're considering are so narrow that they're really occupying the entire space of our region. In fact, as number of rectangles goes to infinity, as we saw last time, the exact signed area is achieved because we have error going to 0. Right. Now, having said all of this, what becomes exceptionally cumbersome and verbose to express is what is in those parentheses, the exact signed area between the graph of function and the x-axis on the interval a comma b. That is clunky and cumbersome. And in fact, that is exactly where this phrase definite integral comes into play. So a definite integral, so I guess today's video is specifically about an introduction to definite integrals. A definite integral is just a symbolic expression to replace the expression for the exact signed area between a function's graph and the horizontal axis. So what I'm going to do is I'm going to take this exact signed area between the function's graph and the horizontal axis and just replace it with a more concise notation. A more concise notation which will ultimately express the exact same idea. So it's got to talk about the function f of x, and it's got to utilize the endpoints a and b, but here is the notation for the exact signed area between a function's graph and the horizontal axis on the interval a comma b. So when we see this notation henceforth, we should always be thinking about this notation as the exact signed area. So it's the area, well, the signed area below. Where does this notation come from with this f of x dx? The idea here, I suppose, let me just draw a bubble of thought. The idea is whenever we were running our approximation using rectangles, we had a summation that would look something like this. Say we have n rectangles, we would just have like fx sub I times delta x, where here delta x is like the width of each rectangle, right? Because like when you talk about each of these rectangles, they're just like a tiny width of the x-axis wide. And so you could think of the height and the width of each of the rectangles in your approximation in this form. And so when you add up a bunch of those heights and widths, here you are. Now, this notation is actually very much related because you see there's an f and then there's something involving x. Well, in fact, d is like the lowercase version of this delta, which is like a capital D from the Greek alphabet. So you can see the analogy here whenever you write them out next to each other. The idea being that as you let number of rectangles go to infinity, this delta x becomes very tiny. The width of each rectangle becomes extremely small. And so if we let capital D go to little d, that just makes sense in some sort of conceptual way. And so then the f of x is just simply replacing it, and the a and the b are denoting the boundaries of the interval. So this is a notation that we will see many, many times this semester, and the value of the notation is that it is just a concise way to express the exact signed area between a function's graph and the horizontal axis on the interval of interest. But I will say this, as soon as we have this notation, we can actually start to develop some ideas related. So what if, let me just, as sort of example sort of properties, we'll go through more properties in class, but sort of some sample properties, if you will, to get us started. Well, what if you were computing the integral from a to b of 2 times f of x dx? Right? So this is not our function f of x, but now this is a function where every function value is multiplied by 2. Well, what's the effect of that? Essentially, the function is going to be twice as tall, right? You can almost imagine up here, you'd have the function 2f of x, right? It would be essentially twice as tall as the function f of x. And so how much area is contained beneath it? Well, if function f of x contained as much area as it did, the function that is twice as tall is going to contain twice the area by virtue of every rectangle associated with its approximation being twice the height. And so ultimately, this expression would turn out to be twice the integral from a to b of f of x dx. So essentially, a function which is twice the height would have an area that is twice the area. Or in general, you could say something like the integral from a to b of whatever constant times f of x dx would be equal to k times the area of the original. And so, yeah, here's an example of a property of definite integrals which we can deduce based on the establishment of the specific notation, which is, well, kind of nice. Another one that we could mention just to offer us an additional insight, what if we had something like this? Assume f of x was greater than or equal to g of x for all x. Well, that essentially says that function f is above function g everywhere. So if you want to imagine function g, you can imagine function g maybe hanging out below here. Well, since function g is below function f, there's going to be less signed area beneath it. You can even imagine the signed area under g. Well, it's got to be less signed area than the signed area under f because f takes bigger function values. Essentially, if you're looking at the rectangular approximation, the height of every rectangle of f is greater than the height of every rectangle of g. So what would be the case here? Well, if this was true that f was taller than g everywhere, well then we would have that the integral from a to b of f of x dx would have to be bigger or equal to the integral from a to b of g of x dx. And again, that's because if the one function is taller than the other, then the one function contains more signed area than the other. So here are just two properties looking at that we can see are manifestations of this idea of utilizing this definite integral notation. So from some point of view, definite integrals are just a notation, but in some sense, by articulating the exact signed area between a function's graph and the horizontal axis in this concise notation, we now have a way to quickly think about and symbolically think about various ideas associated to where now we're sort of cooking up, at least initially here, two properties related to definite integrals, and the list can go on from here. So we've sort of just unlocked access to a nice way of thinking by having this very concise notation to describe this very specific thing which we've been focusing on all semester long.